Today is try to finish up the clustering, and maybe we'll start the undirected graphical models, depending how it goes. So what have we done so far? Well, we've talked about density clustering, and we've talked about k-means clustering. We talked about, what else did we talk about? Did we do, we did hierarchical clustering? Yes. Yes, no. We got a few yeses and nos. Covered part of it, that means. All right. Yes. Yes, I think we did. And now I want to talk a little bit about spectral clustering, which is a more recent technique. It's still in the yet to prove itself class, I think. I'm not sure whether it can do things that other methods can't do, but I think that remains to be seen. Jisoo is joining us today. With a present. These are the assignments?
Yes.
Okay, I'll give them out at the end. Okay, okay, thanks, Jisoo. Okay. All right, so what's spectral clustering? So spectral clustering works like this. We're going to have some data we want to cluster. Actually, one of the advantages of spectral clustering, though, is it can take fairly arbitrary objects. So really, we're just going to have some sort of objects. Maybe they're images. Maybe they're complicated things. Maybe they're proteins. And the first step is we're going to create some sort of graph where some of the objects are connected or perhaps not connected, something like this maybe. And the graph can have weights, so the edges can be weighted. Let's find a brush. Here we go. So we're going to have a graph G, and we're going to have a matrix W. This is going to be an n by n symmetric matrix. Just think of this as some sort of weights. And so let's start off with just two examples of the kind of graphs people use. So one of them is simply wij is either 1 or 0. So it's the indicator function if xi minus xj are closer than epsilon. So this is very much like single linkage clustering, right, where we formed a graph if two things are within epsilon of each other or not. Another common choice is the Gaussian kernel. So this would look like xi minus xj. There's going to be some sort of tuning parameter here. They're both some measure of similarity. If x and I and xj are close, this will be large. If they're far away, this will be small. And in this case, we'd have a completely connected graph, but it's just that some of the weights would be very small and some of the weights would be very large. All right. And now we're going to, for every node in the graph, for every observation, we're going to sum up the weights, which is called the degree matrix. So we're going to define dii, which is just the sum of all these weights of the things it's connected to. J and then we put these into a diagonal matrix, the degree matrix, and 0 off the diagonal. Okay. And now what do? Well, we take this matrix W and this matrix D, and we form this matrix. And some of you will have seen this before, but if you have not, it may look a little bit mysterious. And there's different versions of this matrix, but I'll use this one for the moment. It's D minus W. And this is called the graph Laplacian. How many of you have seen graph Laplacians before? Oh, probably about half of you. OK. If you've taken any sort of graph theory, probably you would have come across it. And this graph Laplacian we're going to use to do clustering. So let's look at the properties of this guy. Well, first of all, we're going to form the this is a matrix, an n by n matrix, so we can look at the eigenvalues and the eigenvectors. So we're going to look at lambda 1, sorry, lambda v. This will be an eigenvector with corresponding eigenvalue lambda. And so what we're going to do is get all of the eigenvectors and eigenvalues. So think about it this way. I'm going to actually, sometimes we order them from largest to smallest, sometimes from smallest to largest. In this case, it'll be convenient to order them according to smallest to largest. And the corresponding eigenvectors will be v1, v2, vn. OK, so all we've done is take this mysterious matrix. We can do its eigendecomposition. What's the point of this matrix? And the key is this theorem 19 here on page 33, which if you don't have your notes, let me just put it on the board for you, which says that this graph Laplacian matrix has the following very interesting properties. First of all, if I take any vector, so the way to think about this is, let me put a simple graph over here. So that's kind of a really simple graph. Now think of defining a function on the graph. What I mean by that is just attaching a real number to every node. So just think of this as, if you have data, this is just a function over your data, but it's only evaluated at your data points. Then the graph Laplacian has the following properties. Well, first of all, it's easy to check this is symmetric and positive definite. And that for any such vector, F transpose LF, so if I just take this product, it's nothing other than the double sum of the weighted differences. In other words, this is something like a derivative of this function with respect to the graph. It's measuring, in some sense, the smoothness of this function with respect to this graph. Because you can see if two things are close together, let's say these have high weight, then we're putting a big weight on this difference. But if two things are far apart and this is 0 or small, it's putting very little weight. So anything that has abrupt changes locally over the graph is going to have a value of this as large. So that's kind of like saying it's unsmooth with respect to the graph. It has a big derivative. So you can think of that as kind of a measure of how much f is changing with respect to the geometry defined by the graph. This is the key property of the graph Laplacian. It's playing a role sort of like a derivative in some sense, but in this graph world. Okay. These things are all proved here, by the way. If you want to look at the proof, the proof's very short for all of these properties. So keep that in mind. Here's another interesting property. The smallest eigenvalue is always 0. But there may be more than one 0. And in fact, here's the really cool thing, is the number of zeros. So the eigenvalues might look like this. You might have, say, lambda 1 equals lambda 2 equals lambda 3, all equal to 0. And then maybe lambda 4 is bigger and lambda 5 is bigger and so on. The fact that more than one of these equals to 0 corresponds exactly to the number of connected components of the graph, the number of clusters. Okay, so the number of connected components of G is the number of lambda j's such that lambda j is equal to 0. Okay, and again, the proof is right there if you want to see it. But so you can see immediately this graph Laplacian is giving us some sort of information, obviously, about the clustering. It's a little bit less obvious what it's doing for the higher eigenvalues and higher eigenvectors, and what happens if the graph, if it's complete, what's it doing, and so on. But at least in simple cases like this, it's clearly finding for you the connected components. In fact, this is nothing other. If we use the first matrix I put up, which was the one like this is nothing other than single linkage clustering, or hierarchical clustering. And this is just a way to find, another way to find the clusters from single linkage clustering for a particular level epsilon. Okay, but let's try to get some feeling for what's going on more generally. What do the other eigenvectors and eigenvalues represent? And the key is that, remember, what this thing is kind of measuring is smoothness in some sense. And some of you, I don't know if from analysis, you may have learned about the Laplace-Beltrami operator, which is a continuous version of this thing, which is if I have an operator which measures smoothness on continuous things, and I find the eigenfunctions and eigenvectors, what that does is it gives me a basis for a space where the lower eigenvalues correspond to smoother functions. And what's happening with the graphs is exactly the same thing, only it's a discrete version. And if none of that made sense to you, don't worry, because this example I'm about to show you at the top of page 35 if you have your notes. If not, I'll draw it for you. Really shows you what's going on. So this is another graph like this. What I've done is I've just constructed a simple graph where these are all connected. And then there's a second very large component of the same structure. So if we can understand what's going on in a simple graph like this, it'll give us quite a bit of intuition. So here's what happens. I now take the W matrix, I construct the graph Laplacian, I find the eigenvectors and eigenvalues. Okay, so what we're going to see, right, is that there are two eigenvalues that are 0. What are the corresponding eigenvectors? What they are, and what I'm going to do is I'm just going to keep drawing this. I'm going to draw this like this. So this is supposed to be all the dots here, all right, just so I don't have to keep putting it. What's going to happen is that the first eigenvector corresponding to lambda 1 equals to 0 looks like this. In other words, it's just the indicator function. It's just doing this. It's just the indicator function for the first cluster. The second eigenvector looks like this. Okay, it's just identifying for you the second cluster, the second connected component. But now the question is, there's more eigenvectors and eigenvalues, the third, the fourth, the fifth. Roughly speaking, what's going on is, what those are doing is, within the connected components, think of that as splitting the space into pieces. Within each piece, suppose now I want to construct a basis for that space. If you were doing a continuous problem, what you might do is, I don't know, like a Fourier basis, right? Sines and cosines. And that's exactly what's happening. If you look at the eigenvectors that correspond to higher and higher eigenvalues, what's happening is, I'm just going to kind of draw them roughly, is the first one sort of looks like this, the second one kind of looks like this, the third one goes like this, and then you get the same thing over here. You get like a sine wave over here, and then a higher frequency sine wave over here, and an even higher frequency sine wave over here. It's just splitting the space into connected components, and then within connected components, these are not really continuous curves, right? These are actually vectors because it's discrete. But I'm just giving you a cartoon version. The point is, you're forming an orthonormal basis, and with respect to this notion of closeness defined by the graph Laplacian, you're going from smoother to less smooth functions, or smoother to less smooth vectors, I really should say. So this is supposed to be the discrete version of, again, just taking like the unit interval and creating like a Fourier basis using sines and cosines. But here, in the real space, closeness is the Euclidean distance and so on. Here, the notion of smoothness is coming from this graph and the corresponding graph Laplacian. So this is useful not only for clustering, but also we'll see later on when we talk about dimension reduction techniques. You might take high dimensional vectors and represent them in this basis, maybe project them onto the first few eigenvectors to get a low dimensional representation. That's one of the dimension reduction techniques that we're going to talk about. Okay, so that's the simplest version of this eigenclustering, or this spectral clustering. Now, there are other matrices, L, besides L, that people use. If I did not have a simple 1, 0 adjacency matrix, like I had in the graph over here. It's less clear how to interpret the eigenvalues and the eigenvectors. And there are more choices, too, how to construct this thing. So there are, I would say that that particular version of the graph Laplacian is actually used quite a bit in certain branches of CS and graph theory, but not so much in machine learning or statistics. It turns out, as n goes to infinity, the asymptotic properties of this graph are not so good, of this graph Laplacian are not so good. And so people have devised other ones, and there's a whole bunch of them, but I'm just going to describe a particular one that has a very nice interpretation. Instead of taking the difference, it looks like a small modification. I'm taking D inverse, that's easy to compute because it's a diagonal matrix, times W. This is called the random walk graph Laplacian. Some people put an RW here for random walk. And it has very similar properties, which I've listed here. The eigenvectors of this are related to the eigenvectors of the other one. The first eigenvalue is 1 now, not 0, and so on. So there's like a change of scale going on. But nonetheless, this is similar to that thing. And again, we can do an eigen decomposition of this thing, and you can think of it as forming a basis corresponding to this graph. But what's the interpretation of this? But the nice thing about this is, and I think this goes back to Koifman, as far as I know, it has a very, very nice probabilistic interpretation. So remember that really what people use in practice is some sort of kernel. The 0-1 thing is not so useful in practice. More likely people, well, it depends on the application, of course, but I'd say it's more common to have some sort of Gaussian kernel or something like that. Think of this again as a measure of similarity. That's big when two things are close so that they're similar. What is the interpretation of this thing? Well, actually, if we think about what does the ith element of this look, let's look at Lij. This is going to actually look familiar. Over the sum of the weights. This should start to look familiar, right? Looks like a kernel divided by the density estimator. In fact, if I multiply the top and the bottom by 1 over n, I'm going to get 1 over n times the kernel value. And on the bottom, that's just the kernel density estimate at xi. So you can see it's related to that density estimation, but it actually has a very, very specific interpretation. So here's the interpretation. Are you ready? This is the random walk. This is why it's called the random walk graph Laplacian. Imagine, let's put a person here, like at some point, let's say right there. And now let's let this person take random steps. And the probability that they take a step will be simply they're right here. They now compute the kernel here and at the jth point. And we do this for every j. And we take a step with probability proportional to this. So in other words, if I evaluate the kernel value between here and here, here and here, here and here, here and here and here, I get a bunch of numbers. I normalize them to sum up to one set of probabilities. Now I take a random step with those probabilities. So what's going to happen is I'm going to take a step, say, to here with high probability, maybe over to here with lower probability. A step from here to here would be very low probability. Okay? And so what happens is I take a random step. I started here. Now maybe I go here. Now I repeat the process. I start here. I compute those probabilities and take a random step. What you've constructed is simply a Markov chain. And you can see that this L is just, in a Markov chain, we have a matrix that describes the transition probabilities. That if you're at this, what's the probability of going from point I to point J? It's just the number here, that's precisely what this is. Now, why do we care about a random walk on these points? We're not, and one thing I want to emphasize about the random walk graphoplasty, we never actually run the random walk. This is just a conceptual device. But this is a way of, in some sense, measuring distances that are sensitive to the density. Because what's going to happen is, if you imagine just hypothetically running this, if you imagine running this random walk, what's going to happen is, let me draw an example. Let's say I have a set over here, then it's got a thin connection with some other set over here. Just imagine there's lots of data over that set. In terms of Euclidean distance, let me actually make this larger. In terms of Euclidean distance, from here to here is the same as from here to here. But if you imagine running this random walk, you can see that if I let this random walk go, it's going to have a very easy time getting from here to here, because there's a lot of possible paths here. To get from here to here is very difficult. It's got to get into this little narrow region, go over here, and so on. And so what's happening is the random walk is measuring the connectivity of the data. It's measuring which pairs of data points are highly connected and which ones are separated. And so this matrix L has all kinds of nice properties. And these properties reflect the geometry of the data, in the sense that basically if I now take the eigendecomposition of this, it's taking into account some notion of distance, but not the usual notion of distance, not Euclidean distance, but distance in terms of how the data are actually distributed. It's some notion of density distance. It's like saying these two things, roughly speaking, it's saying these two things are close because there are many, many, many paths connecting them. But this point and this point are far away because there's very few paths connecting them. And so it turns out that this can be made precise. Quakeman had a whole series of papers about this. Sometimes this is also called a diffusion, by the way, instead of a random walk. And so this is sometimes called the diffusion kernel. And this is just creating a basis for you, if you do the eigendecomposition, that's respecting the geometry of the data. And so now if you project the data onto the first few eigenvectors of this, you're somehow getting a representation of the data that's lower dimensional, and that represents the structure of the data. And we can use that for dimension reduction, but also for clustering, as I'll show you in a few minutes. So the typical way to do the clustering here again is we're going to do, again, an eigendecomposition. So we're going to get eigenvalues and corresponding eigenvectors. And I'll show you an example in a minute. And then typically we just take each data point now and we pick some dimension. So we're now going to project. This is like doing PCA, except we're using a basis constructed from this matrix. We project it onto, say, some small number, let's say k eigenvectors. And the hope is that somehow we've now captured the structure of the data, and we can just apply ordinary clustering, like k-means clustering, to these projected data points. So there's a lot of steps here. You have to choose a kernel. The kernel often has a tuning parameter in it that has to be chosen. You have to decide how many vectors you're going to project onto. You now project the data into this spectral world. Now you have to decide what algorithm to run, and there might be tuning parameters there too. Okay? So I know this can sometimes get a bit confusing, so let me just show you again a few examples. So the first example is at the bottom of page 37. It's a made-up example, but I want to show you the magic that happens when you do this. So if you don't have your notes, I'll just show you. The data are two rings. That's one, and that's another one. And what we know is that if I just did, say, k-means clustering, that's not going to work well. there, right? So I'm going to apply this algorithm. I'm going to compute this matrix. And what I've done is I'm using a Gaussian kernel. I've picked a particular bandwidth for the kernel. I compute this matrix. I compute the eigenvalues and eigenvectors. And what you see, the second plot shows the eigenvalues. So the first one's always 1. And then they start to die off pretty quickly. The idea is that once the eigenvalues die off, there's not much information left over. We'll talk more about that when we talk about principal component analysis. But once again, what ends up happening is the first couple of eigenvectors separate the clusters for us. So if I do I have a plot here of the first eigenvector versus the second eigenvector, and this is what the data look like. You see what's happened is I've gone from this nonlinear structure, and by doing this spectral decomposition, I can untangle very easily now, right, the two components, the two connected components. I could run here, single linkage clustering or k-means clustering might even work, whatever. What are the higher order vectors, eigenvectors? Same thing. Within each component, it's constructing something like a sine and cosine basis. As I go higher and higher, I get functions defined over those components that are getting more and more wiggly. I've actually plotted some of those vectors for you. But you can just think of it as creating a basis whose smoothness properties decrease as we go to higher and higher values with respect to the geometry of the data. Okay? Let me just give you an idea how you would actually use. Yes?
What exactly is this plot for?
Which plot are we referring to? Oh, this is the first eigenvector versus the second eigenvector.
What exactly are they?
Well, so remember, I have this matrix.
The coefficient on the first eigenvector.
I think it's actually maybe the second versus the third one. But I'm taking this matrix. Now I'm finding the first eigenvector, second eigenvector, and I'm just showing you what the values are of
The actual coefficient.
yeah.
In what sense the second definition is more convenient than the first one?
It's not that it's more convenient. It's just that when people have looked at the properties of these things, they say, what happens when n goes to infinity? The original graph Laplacian doesn't converge to something nice. Whereas this second one actually converges to this thing I talked about earlier. So it converges to a well-defined operator. And the operator has very nice properties and so on. So it's just that it has limiting properties that seem to make good sense. There's a paper about this by, what's her name? Von something. Maybe if I... Von Luxburg. She has a very, very nice tutorial about all this stuff. And she talks about all the different definitions people have put down for these different graph Laplacians and how they behave when n gets large, and which ones behave well and which ones don't.
Larry, I have a question. How do you know you can have it at 2?
Well, that's a big problem. Well, we're going to come talk about that later.
There's another question.
Yeah.
You know, the first one, we actually knew intuitively the dimension of the null space actually gives us the number of components, right?
Yeah.
So here, is there something that we can just immediately say, this is a cluster of 2?
No. So, yes, if they're disconnected, you'll get very similar behavior. But in general, no. And that's going to come down to how you choose the tuning parameters. So I'm going to come to that point in a minute. Yeah. I just want to first out. Yeah.
Problem regarding the representation is the n factor. One is the axis.
I just ordered them. I just made an arbitrary. I
Order
ordered.
a kind of like index. Or
That's right. It was just an index. So
it's along the outer range into the
right.
outer
So let me explain that. That's a good point. So for those of you who are looking at 38, and I'm plotting these vectors by plotting, one number at a time. How did I order them? I ordered them by going around the outer ring and the inner ring. If I had put an arbitrary ordering, it would have looked terrible, right? So I used knowledge of what the truth was to make sure that the vectors had clear meaning. Let me explain how this is used in practice. Suppose I'm taking, I want to classify some images of, say, take the famous zip code data where they have handwritten digits. People wrote numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So each image is a bunch of pixels. I think there were 16 by 16 in the original data set. So I have, if I stretch this out into a vector, I have for every digit, every data point is a vector in R256. And I'm trying to classify, was this a 2 or whatever. Now you can run lots of classifiers on high dimensional data, that's no problem. And if I just wanted to cluster them, I could just run k-means clustering or whatever your favorite clustering algorithm is. But you might want to reduce the dimension first. And you might want to try to do this with spectral clustering. So what I did was I used the Gaussian kernel. And then I just retained the first. So I projected the data onto the first 2 eigenvectors of this matrix. And again, I've produced a plot for you. So remember, every data point is 256 dimensional. Now I'm reducing it to a 2-dimensional data set because for each data point, I'm only retaining its projection onto the first and second eigenvector. And what the data look like, amazingly enough, so I'm going to give you the artist's reconstruction in case you can't see it. These are all, this is what the data look like. And then since I did this without knowledge of what the digits were. I only used, by the way, the digits 1, 2, and 3. Now I'm going to color these in according to what the true digit is. And these turn out to all be, which ones are the red? I don't remember the coding. But these are all like all 1s, all 2s, and all 3s. So what that shows you is if I use the first few vectors of this eigenvectors of the random walk graph Laplacian, and now if I applied a clustering algorithm, I'd very easily be able to cluster these into 3 groups. Or if you're doing classification, this would make classification much easier because it divides so cleanly into 3 groups. This is quite a success story, right? That this thing seems to have worked somehow. OK, so the bottom line is we choose one of these graph Laplacians. You do an eigendecomposition. You project the data onto the first few eigenvectors. And now you do something with that, either classification or clustering. Since we're talking about clustering, actually, I guess we should say you do clustering on that.
Here, the projection onto the eigenvector space is that you'll construct a new vector based on the coefficient.
That's right. Yeah.
It's not the normal projection.
It is the normal projection. It's going to be just like.
But when you change the space, if you just do projection, I did that. You cannot change the space. You use another basis.
Well, we get the basis first from L. That's fixed now. Now I take.
But later when you cluster, you change the space.
No, I don't. I have my. Let's suppose I decide to use the first 2 eigenvectors. Now I can take each data point, which was originally in 256 dimensional space, and write it as a linear combination of these 2 eigenvectors, the one that minimizes the distance to the original vector. So now I have a 2-dimensional representation of the first digit, and I do that for each digit. I'm not changing anything. I'm really doing PCA. I'm just not using the usual Euclidean basis. I'm using this graph Laplacian basis.
I just want to understand how do you change the 2 rings to 2 lines. Here, the dimension is only 2.
That's right.
And why there are so many eigenvectors?
The total number of eigenvectors equals the dimension of the original space. But I'm only going to use the first few of those to represent the data. So I've done a dimension reduction. I probably should have covered the spectral stuff after I did PCA, which is one of the next topics. But so I'm just doing PCA, for those of you who know what PCA is, but just using a different basis. We'll come back to this point. It'll be clear when we cover linear dimension reduction.
When people talk about manifold learning,
Yeah.
they usually mean this.
So
Is this
there's some confusion here because this stuff is used for more than one thing. It could be used for trying to identify a manifold if the data lie in a manifold. It could be used as a dimension reduction technique, and it could be used as a clustering technique. In all cases, what it's trying to do is find some data-dependent reparameterization of the data. And then it's used for many different tasks. And we will talk about the manifold learning case when we do nonlinear dimension reduction techniques. So yeah, there's a little bit of fuzziness here because the same basic techniques are getting used. I was trying to just focus here on the clustering aspect. Now let me say that for now, just think of it as an algorithm for doing clustering. But to me, I have to admit, as with a lot of these things, I have a little bit of skepticism because there's an awful lot of choices of parameters to pick here. And I haven't seen any papers that tell me how to pick these parameters. And the example I did here, I had to do 20 times before I got values of the parameter that didn't just give me nonsense out. So if you think about the 2-ring example, we already know that density clustering would have worked perfectly on that, right? That's a beautiful example for density clustering. Density clustering has one parameter, the bandwidth. Here, we have to pick the kernel, the bandwidth, the number of vectors to project onto, and then there's some clustering method you're going to apply once you project onto those vectors, which also involves tuning parameters. So there's at least 4 tuning parameters, maybe more. And it seems very sensitive in my experience to all of the choice of all these tuning parameters. So I don't know. I've yet to see an example. I know people get really excited about spectral clustering, but I've yet to see an example where it's really clear what the tuning parameters are to choose and where it does better than existing techniques. And by existing techniques, I mean you have to include things like density clustering. It can beat k-means clustering for sure, but whether it can beat density clustering with a carefully choose bandwidth is an open question. So I actually posed this question to someone I know who's worked on spectral clustering. I said, can you actually make a formal connection between spectral clustering and density clustering? Because they seem very similar. After all, they both use this like a Gaussian kernel. The answer I've got so far is sort of, that they're still working on it. Okay, so that they haven't sorted this out yet. So I think it's kind of unclear what spectral clustering is doing in general. In the manifold case somebody asked about, you can prove actually that if you choose the right graph Laplacian, and it is converging to something called the Laplace-Beltrami operator, which is something that is used in manifold theory. So there are some cases where it's understood what the spectral methods are doing. But in general, with lots of messy data, let's say, it's not clear that one can say, there aren't any theorems I know of that say it's going to produce a good clustering and it's going to be better than such and such a method. So nonetheless, there's something interesting about it, so I think it's worth exploring it more, and I'm glad people are working on it. But I'll just warn you, when you go to do this in practice, unless maybe I'm just really bad at it, but in practice, I think it's hard to tune these things and make them work well. At least that's been my experience. So we'll come back to these spectral things again when we talk about dimension reduction. I was really torn whether to put it here or put it there, so I think I'm going to cover it in both sections. Dimension reduction is probably what we'll cover after we do graphical models.
Especially in this case with the digits. So this seems like we could have used, say, cross-validation because in the end maybe we care about the classification of this.
Yeah, that's a good point. If the ultimate goal is classification, we're in great shape. You can choose all your tuning parameters by cross-validation. But if we're in an unsupervised situation where we're just trying to find a clustering, it's very unclear how to choose all these parameters.
Can we say that the spectrum clustering being something of the nonlinear reduction on data, because you have just to show us that there is like a double ring data, and after the mapping to the first vector and the second vector, we could get them separate.
Yeah, that's true. So you could just view it as a dimension reduction technique, which, as I say, we're going to talk about. We're going to revisit this when we talk about dimension reduction. But purely just in terms of clustering, it's a little bit harder to say what it's doing. I suspect what it's trying to find is actually low density regions that separate high density clusters. But as far as I know, nobody's actually proved that in general. I think you can prove that in special cases.
It seems that spectral clustering is a mixture of PCA
Yeah, that's a good way of saying it. Yeah.
Then what is this superiority? You mentioned mixture is actually the triads.
Yeah.
Yeah. So, but what is the advantage over the other two?
Well, when we revisit these spectral techniques, we're going to see that these spectral methods, another way to think about them, actually, like he just said, is it's just a non-linear dimension reduction technique. So another way to view all of these things, and we'll get to this later, is there are things like multidimensional scaling, which are linear methods for reducing the data, and a lot of these spectral techniques can be thought of just as kernelized or non-parametric versions of multidimensional scaling. So basically, kind of more non-parametric dimension reduction is probably a better way to think about it. Maybe I should have done dimension reduction first and then clustering. I probably would have been pretty clear. Okay, so
I still have trouble understanding that projection. Here, if data xi has its own dimension. For example, here we have 2. But those eigenvectors are of dimension n.
yeah, so let me.
So how do you project the dimension 2 to a dimension vector? Dimension n times k.
Well, there's the dimension of the space. This. Maybe we should talk about this when we do dimension reduction, because there's a dimension. Anytime you do these projection methods, there's 2 dimensions. There's the encoding dimension and the decoding dimension. So I think I know what's confusing you now is that, do you know PCA? Yeah, so you know when you do PCA, suppose I had data that looked like this, and I find the first principal component, and now I project, say, this point here, and I project this point here. There's 2 representations of the projected data. There's the coefficient onto this vector, which is one-dimensional in this case. I've taken a 2-dimensional data set and I've represented it as a one-dimensional object. Or I can represent it actually in the original space as this 2-dimensional object, which happens to live on a one-dimensional subspace. And that's always full-dimensional.
I guess the confusion is that you have your objects live in some space, but once you define the kernel, it's just you have like this kernel matrix. And that is like an example by an example. So it's kind of the dimension of the original objects kind of disappears once you have the kernel matrix in some sense. Right?
That's right. So because this thing is always n by n. And the vectors are high, but each of the vectors, just to be clear, when we're projecting onto those vectors are n-dimensional still. But the number of vectors you're projecting will be much less than that. So it's just like saying, do you consider this a one-dimensional representation or a 2-dimensional representation? I don't know if that clarified it or confused you. Let's move on because it's not. We'll come back to that point again when we do dimension reduction. It's not a huge deal. I can tell he's going to obsess about this the rest of the time. All right. So we've been through a lot of methods, and that's enough methods. I mean, we could keep going, right? There's thousands and thousands of clustering methods. There's new ones that are invented every day. I just want to mention 1 or 2 other last points, okay? So here's a really interesting problem that to me is still somewhat unsolved, which is in regression analysis, if we have a high-dimensional regression problem, what we might do is some sort of variable selection, right, to reduce the dimension of the problem. So the question is, how do you do variable selection for clustering? Instead of, let's suppose I have 5,000 genes measured on each person and I want to cluster people. This is very common to do in bioinformatics. Do I really want to use all 5,000 genes to cluster everybody? Well, probably a lot of the genes are irrelevant. So I might want to use a subset of the genes. And I think this is still an area where I would consider this an open problem. There's been a lot of proposals put out there. So let me just mention a few ideas. So let's imagine we have a big data set like this. So this is the number of people by the number of features. And again, I want to choose maybe a subset of features on which to do clustering. So how are we going to do this? Well, one idea, probably the easiest idea you might think about, is to do some sort of screening procedure, by which I mean we look marginally at each feature and say, can we see which features are important? Okay, this is a very popular technique. So just to be clear, this is feature 1, 2, up to D. So what we'll do is we'll start with feature 1, and we'll just look at that data set. So just think of it as some sort of histogram. And maybe we'll take feature 2, and maybe its histogram looks like this. And I think if we look at this, we might think, well, maybe intuitively, feature 1 is not helping so much with the clustering. Feature 2 is. And there's a way to formalize this by doing some sort of test for whether is the marginal distribution of each data set, is it unimodal or not? That might be one way, right, to decide whether this is a useful feature or not. If it's unimodal, it doesn't seem to provide much clustering information. If it's not unimodal, then it would seem to provide information. How do we decide if something is unimodal or not? So let's just talk about that in general. Suppose I have n observations from a distribution. Let's suppose we'll rescale it so it's on 0, 1, just to keep it simple. How do we test the hypothesis? Actually, let's call this CDF F. How do I test the hypothesis that F is unimodal versus not unimodal? Unimodal means like the density is going to go up and then go down. And so the answer, it's not the answer, the first answer, and probably the most commonly used answer, is something invented by John Hartigan. John Hartigan is a character I haven't mentioned before in all my discussions of interesting people. Hartigan's a very interesting character. He's at Yale. He did some of the earliest work on clustering. He wrote a book called Clustering, which was one of the first books on clustering. He did some of the most fundamental work on k-means clustering and other versions of clustering. So if you ever look back at papers and older papers on clustering, you'll often see the name Hartigan. He invented density clustering. He did a lot of interesting stuff. And for him, clustering was sort of a side thing. He was more of a mathematical statistics guy. And so he also has a lot of important theory in mathematical statistics. He also defined the first test for this that I'm aware of. It's called the dip statistic, because what it's looking for is there some sort of dip in the CDF? And how do you define the dip formally? Formally, it's defined the following way. So here is some given CDF. Script U are the set of all CDFs that correspond to unimodal distributions. And what I do is I take the distance between F and G, this is a unimodal distribution, and I find the closest one. So this is measuring how close is F to being unimodal. And then what we do, the test statistic, is simply to compute the dip of the empirical distribution. That defines a thing. Surprisingly, there are fast algorithms to compute this. If you just think about it offhand, how am I going to find that? How do I take the info over this whole class? But what makes this paper so clever is he finds a very fast algorithm to actually compute this thing. And you have to get its distribution. What's the distribution under the null hypothesis? The distribution is somewhat complicated, but it can be found. And so basically you can find a critical value, C alpha, such that if H naught is true, the probability that Tn is bigger than C alpha is alpha. This is built into to R. I forget the name of the function, and again, I can't tell you what it is in MATLAB. I'm not sure if this is in MATLAB or not, but it is in R. Yes?
Sir, what's the meaning of a CDF being unimodal?
What's the of a CDF being unimodal? That's a good question. It has to have, let's think about what the density looks like. So it means it has to be, so the CDF has to go up, and then it has to have a change like this. And so I think it means, that's a good question. I've kind of forgotten. I think it means it's concave. What's the definition of unimodality? So, okay, so if the density is increasing here, then what does that mean about the CDF? So think about it this way. The density, let's pretend it as a density, and it's increasing to some point and decreasing to some point. That does imply something about the shape of the CDF, and I have to admit I'm forgetting what it is right now. It's something.
It's defined in terms of the corresponding PDF.
Actually not. It's defined, it doesn't have to have a PDF. But it's easiest to think about it that way. And
Is it just second derivatives like negative or something?
no, it's something about concave majorants or something, some geometric thing like that. And I'm forgetting, I'm sorry, I'm forgetting what it is right now. But the easiest thing to think about is, let's suppose there is a density, and that the density increases up to some point and decreases at some point. Or that it's monotonic, either case. Whatever the shape of that corresponding CDF is, that's called a monotonic CDF. Now, I'm sorry, I forgot the precise definition.
So if the density has like a little dip in it,
Then it's not,
be not unimodal.
yeah.
The unimodal is the change is monotonicity only one time.
Right.
Represent-
That's right. You can't have two changes.
How does the term dip comes into being? Because actually,
So that's why I was trying to draw the picture here, because it turns out that it corresponds to whether there's a dip in somewhere in the CDF, but I'm just not remembering well enough how to create the geometry. My picture of the CDF here is not good enough to illustrate that. There's something to do with a dip, which is why it's called the dip statistic. Something like there's some sort of dip like that.
But the CDF never dips, right?
Oh, a good point. It does, but it has to be a non-decreasing dip. Yeah. But I've got to check. I've got to remind myself what the exact connection is between the dip and the thing. Yeah. So the amazing thing is that this can be computed at all, actually, but it can be computed very quickly. And this gives you a well-defined hypothesis test for whether the distribution is unimodal or not. Okay? So now, you found it.
Yeah, it's a paper.
You found the paper
Old paper, deep, what's it called? Deep test of unimodal.
by Hartigan.
Yeah.
Hartigan and Hartigan. That's it. Yeah.
So there are a couple.
That's his wife. She's an epidemiologist, and I think it's one of the only papers they wrote together.
That's how they get married.
Yeah. So that's the paper. Yeah.
Okay.
Yeah, check the paper, because I'm sorry, I'm having a senior moment. I've forgotten the exact definition. Okay, so how do you apply this, though? So very simple. You take each column and you run the dip test. And there are other tests for unimodality, by the way, but the dip test is particularly fast and simple. And now you find out which ones are rejected, and those are the ones you keep. That's the idea, right? If it's unimodal, you say that's probably not informative, I'm going to throw it away. If it's not unimodal, if I reject it, I keep it. Okay, that's the idea. Now, here's a question. Does this work? Do you think this works? Is this going to find the relevant variables for clustering? It has some intuitive appeal. Well, the answer is sometimes. Because Let me show you 3 examples. Actually, just before we do that, let's back up a bit and let's think about high-dimensional regression. To do high-dimensional regression, we do things like what? Forward stepwise regression or the lasso or something like that. We never did marginal regression. You could regress y on x1 and decide, does that look significant? Then you could regress y on x2 and say, does that look significant? Then you could do y on x3 and say, is that significant? That's called screening. And people don't usually do that unless, if it's very, very high dimensional. If you have a million covariates, people will actually do that as a first step just to reduce the number of covariates you have to consider. But if you have a moderate dimensional problem, we don't do regression by marginal regressions. We do a joint regression of some kind, right? Precisely because if I'm looking at a regression of y and x1, we're ignoring all the information about the other variables. The same problem you're going to see happens with clustering. So let me show you these 3 examples. Actually, let me start with example 3. Suppose I have just 2 features. And these are I have a really clean data set, looks like this. It does seem like I could do the clustering knowing only x1. In some sense, it seems like all the clustering information is in x1, right? And the screening method would probably work here because I'll get the marginal density of x1 looks like this, so I should reject that test. And the marginal density here maybe is something like this. So we're going to say, OK, x2 won't be rejected. And so we're going to just end up picking x1, and we will recover those clusters. Okay? But what if the data look like this? It seems like in order to recover those clusters, I need both x1 and x2. But these 2 clusters, I've made them, if I've drawn them correctly, when I look at the marginal distribution of x1, it might look pretty unimodal. And this marginal, if I've drawn this right, when I look at the marginal distribution, it'll look unimodal too. So what will happen is I'll never pick x1 because I won't reject unimodality. I'll never pick x2, and I'm going to miss these clusters. The point here is that the clustering structure might be truly multidimensional, and that the marginal information just isn't good enough to identify those clusters. This is just like if I could regress y on x1 and it's not significant. I could regress y on x2 and it's not significant. But jointly, regressing y on x1x might be very important. It's exactly the same phenomenon. Marginal information might not be enough to recover joint information. So this is a case when screening doesn't work, or at least maybe saying it doesn't work is too harsh, because if we miss some clusters, maybe it's not the end of the world, but it definitely is going to lead us to miss these 2 clusters. The other picture I drew is an extreme version of this. Of course, if they're super, super close together, we're going to have the same problem. But arguably, even if you had the joint information, that's not going to help you much either. I tried to make them so close together that they're indistinguishable. So in this case, you haven't really screwed up because having both variables wouldn't have helped. It's really this in-between zone where things kind of get messed up. Doesn't mean it's not going to work. It just means you can construct examples where it's going to miss some of the clusters.
But can we see that in this situation, the 2 variables are both necessary for us to construct?
Sure, but now I have to give you 1,000 variables. And suppose there's 6 of them you need jointly to get the clusters. How are you going to know that? So don't be too fooled by my simple 2-dimensional examples, because remember, real life's going to be really complicated. So I'm not saying screening is a bad method, but you do have to be aware that because of this phenomenon, you have the potential to miss certain clusters. But it does raise the following question. Can't we do the same thing to clustering that we did to regression? Can't we do some sort of maybe L1 sparse thing and so on? There's been a lot of effort to do this recently. I'm going to tell you about one of the proposed methods. To the best of my knowledge, none of them have been shown provably to work. That is, to actually recover the clusters. Some of the methods, in fact, have some theorems, but when you look at the method, it turns out they're actually just doing marginal screening. That is, there's a few papers where they have this complicated thing with an L1 penalty, but when you look at it, at the actual method, it's separable. It could have been done separately on each coordinate, and so it's just another screening method. There was no need to jointly cluster and do variable selection at the same time. So there are some methods that are just kind of demonstrably not doing anything more than marginal screening. But there have been attempts to do something a little bit more principled. And here's an interesting challenge for you. If you can prove something about one of these methods, then you'll have a nice paper to write. So this method is called sparse k-means. The idea is to sparsify k-means, as the name suggests. It's by Rob Tibshirani and this was his former student, Daniela Witten. So let's remember what k-means is doing. K-means is trying to minimize. I'll write it like this. It's, oops, there's a, yeah, minimum, right, over the centers. Okay, that's the usual k-means that we're trying to minimize, right? We have this loss function, the distance of each point to the center. And we take the minimum distance, and we're trying to find the centers that minimize that. We can actually rewrite this sum as the sum over all the clusters. And if I do that, this is actually equal to, I'm going to sum over the clusters. Say we're doing k. Okay, so here's one center, here's another center. I'm going to sum first over this and then sum over this. And you can rewrite this as 1 over nj times the pairwise sum of s and t and aj. Okay, let me explain what I've just done. Here I add the distance from each xi to the nearest centroid, summed over all the data. By just rearranging things, you can actually rewrite that sum as all the pairwise distances within here plus all the pairwise distances within here, just by adding and subtracting things. And I just called that d squared. This is any pair of points in the jth cluster. And to make it work out to exactly the same thing, you have to divide by the number of things in that cluster. So this is just another way to rewrite this. All right, now here's the interesting thing. You think, can I just throw an L1 penalty in here somewhere? That always seems to make things sparse. And that's what they tried, and it didn't work. That was a shame. But then they had this insight, which was really, really interesting, which is, well, there's three, if you stop and think about it for a moment, there's kind of three quantities you can compute here. There's this within cluster variability. That's this. You could compute the same thing over all the data points. I could take each pair of points, sum them up and square them and take the average. What do you get if you do that? That's a good side question. If I take a data set and take every pair of points, let's just even take a univariate data set and look at all sums of squares over pairs of points. What do we get? You get 2 times the sample variance. That's just another way of writing the sample variance. We usually write it as xi minus x bar. But you don't have to do that. You can write it as distances between pairs of points. This is called the U statistic representation of the sample variance. So this is like the within sample variance and then the average of those. We could also take the total variance, which would just be all pairs. And now what's the difference? If I take the total variance minus the within sample variance, what I get is the between sample variance. So I haven't said anything, really. It's just defining a bunch of variances. But here's the observation. Minimizing the within sample variance is the same as maximizing the between sample variances, the distances between the pairs. It's just a re-expression, an algebraic re-expression. So that doesn't seem to buy you anything. But nonetheless, let's write it down. Okay, so let me repeat what I just said. Now, I'm going to define the between sample variance as just the total variance This is just the distance between each xi and each j squared averaged over all the data, minus this thing. So I'm just taking the total variance minus this within cluster variance and defining that to be the between variance. Doesn't seem to do anything. This is just a constant, right? This is just some number. It doesn't depend on the clustering. So really, it's a constant minus this thing. So minimizing this was what we usually do in k-means, is the same as maximizing this. And now here was the insight they had. I don't know how they had this, because I must say, I think a lot of people had the idea of trying to put some sort of L1 penalty in this and saw that it didn't work. And what do I mean by putting an L1 penalty here, by the way? What would an L1 penalty look like? It would mean that the distance squared between two vectors, instead of using the usual Euclidean thing, we're trying to do variable selection. What you could do is just put weights on each dimension and try to put some sort of L1 penalty on the weights. You can see the problem is that I can always take the weights to be 0, make this as small as I want. You get a trivial solution. And I think a lot of people probably thought of that. Let's throw an L1 penalty in somewhere. That will eliminate some of the dimensions. Do it to the usual k-means clustering. Doesn't work. And probably a lot of people just said, oh, I guess that doesn't work. And somehow they had the insight. Let's rewrite it as, instead of minimizing the within, let's maximize the between. But now let's put the weights in. Let's replace d with dw. dw means, I'll call this dw. It just means we put weights on the coordinates. And what they realized was that you're now going to maximize this subject to an L1 penalty, but subject to two other constraints. The WGIs have to be bigger than or equal to 0, and the L2 norm squared has to be less than or equal to 1. That prevents, it turns out, a degenerate solution.
But that is not a convex optimization.
So the problem is, this is not a convex optimization. So the algorithm they use is I think it is biconvex, so that if you now optimize the weights for fixed clustering, that's convex. Conversely, when you fix the weights, well, maybe it's still not convex. I think you do kind of a k-mean step. Yeah, it's not. I don't think it's even biconvex. But basically what you do is you alternate between a minimization step over the weights and then a clustering step. So it's a heuristic solution because it's not guaranteed to go to the minimum. Actually, here's the whole algorithm. I wrote it out for you on 42. And what happens, amazingly enough, is you get a sparse clustering solution. You get out a solution just like in k-means, but some of these w's are going to be 0, which means those variables have been eliminated from the clustering. So they found a clever way to somehow bring sparsity into k-means in a kind of unexpected and non-obvious way, in my opinion. But nobody can show anything about this. So all that's known about it is it's been tried out in many examples. Their paper does some examples where it seems to work very nicely in those examples. So by example, it seems to sometimes work. But as far as I know, to this day, nobody's proved anything about it. It would be nice to be able to show that if you had a high dimensional clustering problem and that many of the variables were not relevant, that somehow this was actually selecting out the relevant variables. Okay? And as far as I know, nobody's been able to prove anything. In fact, as far as I know, nobody's been able to prove anything about the behavior of this thing. All we know is that in simulations, it seems to sometimes do a good job. So this is a really interesting thing, and in the sense that I think it's largely an unsolved problem. People keep coming up with algorithms, but we don't know if they really work or not, except by example. Just to make things more interesting, what you really want out, in my opinion, is a much more complicated thing, which is I'd like to know different clusterings for different variables. So in other words, if these are my, think of these as genes, I might want to say, well, for these genes, these are the clusters. For these genes, there's no clustering. For these genes, oh, there's 3 clusters. Maybe there's no clusters here. For this gene, there's 2 clusters. So you can also try to recast this so that you get different clusters with respect to different sets of genes. But that's even harder than just selecting the relevant genes. So there's an important open problem. I think doing a principled way of doing variable selection for clustering is something that, if you're looking for an interesting problem to work on, that's a good one.
Here the sparse key means, what's the meaning of the sparse?
Because what's going to end up happening in the solution is many of these W's, do I have the W? Many of these W's turn out to be 0, which means you can throw those features away. Doesn't affect the clustering. The clustering only depends on a subset of the features. OK, now the last section in this notes, I almost took them out because we've already talked about this. It's the mixture modeling. We talked about mixture models from a different point of view, the twilight zone of statistics, right? But you can also talk about mixture modeling from the point of view of clustering. And so I just put it there again just for completeness. We're not going to go through it because I've already gone through mixture modeling. Was it in this class or 705? It was this class. OK, see, it all becomes a blur after a while. But we already have talked about mixture models. So it's just there for your reference if you want to see it. But of course, mixture models, as we already talked about earlier in the course, could also be used for clustering as well. And if you just want to be reminded about that, I just put all those notes, including the EM algorithm, which you would have learned in 701, is also there for your review. OK? So let me summarize the big picture here, because we covered a lot of clustering stuff. I think of them as being in kind of 4 groups. There's the k-means, and there are related techniques. There's density-based clustering methods. There's hierarchical clustering, and there's spectral methods. There's lots of other ones, but most of them can be fit into at least one of those categories. There's still a lot of work being done in clustering, especially high-dimensional clustering, and especially this problem about how to do some sort of principled variable selection for clustering. OK, so that really brings us to the end of the clustering, and I want to start moving on to our next topic, which is another unsupervised method, which are graphical models. So, of course, we'll jump into it in detail starting on Thursday. But let me just say a few words about it. Is that I'm going to cover it a little bit differently from how you might have taken it in other classes. How many of you have taken the graphical modeling course or are taking it? OK, so about a third of you, maybe a quarter of you. So there's definitely going to be some overlap, of course, between the two. But a few warning points. I'm not going to cover directed graphs, because you should have had that in 701. I can cover them later if you want me to, but I think you've probably seen quite a bit of directed graphs. Is that correct? In 701, you did directed graphs. Yeah, OK. I think undirected graphs are much more useful. And I'm going to start, though, different than most people who cover graphs start by talking about conditional independence. And the problem is conditional independence is actually a very, very difficult thing to deal with. It's very hard to decide if are x and y conditionally independent of z. To try to do that, especially in a high-dimensional problem, without invoking a lot of assumptions, is essentially an impossible problem. So I think that's the hardest version of graphical models. So I'm going to kind of work from reverse. What we'll do in this, when we cover this, is I'm going to start with what are called marginal graphs or correlation graphs, which are just graphs based on correlations between pairs of variables. But that's also going to give me a chance to introduce something to you, which is something that's happened in about the last 4 or 5 years, which are new ways to measure dependence between variables and between vectors. There's been a lot of interesting recent work on that. How do I tell if x and y are independent? Just a pair of variables. And there's actually been recent work. You would think that would be solved years ago, but there's been some very interesting recent work. So we'll talk about marginal correlation graphs first, and we'll do that in some detail. And that'll also be a chance for me to introduce the high-dimensional bootstrap. And we'll probably say more about the high-dimensional bootstrap later in the course. Then we're going to transition to what are called partial correlation graphs. Then we'll make the jump to conditional independence graphs. We're going to go from the easiest to the hardest. And by easiest to hardest, I'm talking about statistics. How hard is it to solve that problem statistically? So I want to go from the easiest to the hardest. And then we'll talk about all the properties like Markov properties and cliques and things like that. So make sure then that for next time you download the notes or bring your laptop, whatever, with the undirected graphical modeling notes. I have assignment 2, and for those of you who didn't pick up your project description, I'll put that over here. Let me put out the assignments.